This is my video number 35. I continue on giving example on flux. How do we evaluate flux? The formula for evaluating flux is we integrate over s f dot n ds, where we know this is just integrate s f dot our n is negative fx negative fy 1 dx dy. Okay, for the surface as given as z f xy. Okay, now let's look at one or two example in this video. Example, we consider surface S given as z equal to 9 minus x squared minus y squared for z positive. Remember one thing, when we're evaluating the flux, because the meaning of flux is that the anything like a fluid or the vector field passing through some surface. Okay, it means if the our material or our region are not close, then we cannot find the flux. Okay, so look at this example. Let's say we have S, our surface is given as that, and our F is given as 3x 3y and z. Okay, we find flux for of F through S. Okay, so first thing, evaluating those things is not major issue because we just using that formula, but to identify the region of integration is if you're not familiar with, it's quite I would say it's quite difficult. So if you look to help you to identify those limit of integration, we look at the given surface here. For this case, this is the given surface. Okay, and identify which one f, which one. So because we need to identify what our f is. So in this case, this is our f because z is fxy. So our z is, this is our fxy. Yeah, so this is 9 minus x squared minus y squared. So we need to find what is fx and what is fy. So from there we can differentiate respect to x, so that gives you negative 2x. Differentiate respect to y, that gives negative 2 to y. Okay, and now let us find the what is the surface. So if you look at this S here, z equal to those things, so this is in 3 dimension. So let's try to sketch this. Okay, on xy plane, z is 0. On xy plane, z is 0. So what we have is x squared plus y squared equal to 9. This is just a circle with radius 3. Okay, I obtained this from the given surface where z equal to 0 because we consider on xy plane. So on xy plane we have a circle with radius 3. So we have a circle here with radius 3. Okay, so that we have 3 we have 3 here, -3 and -3. So this is a circle of radius 3. Now on z-axis, yz is 0, xy is 0. So if you look at our surface here on z-axis, xy is 0, so you have z equal to 9. So we have 9 here. Okay, and if you proceed on x, y, xz axis, y is 0, so we have z is 9 minus x squared. So you know what is that. So this is this thing. Okay, and on yz plane, we have x is 0, so we have z equal to 9 minus y squared. That one, z equal to 9 minus y squared. So we have from there, so we have that. Okay, so that's our surface now. I hope you can see this. This is there's a circle and so on. Okay, so this is our surface. This is our surface Z, S. Our surface S. So on xy plane, given as x squared plus y squared equal to 9. So remember that this is on our region R on xy plane here, alright, which is a circle. So you should have in mind instantly that if you circle, then we may use this, polar coordinate. Okay. Yeah, should have in mind. If you circle, then we should have used that kind of transformation. Now, come back to our main issue here to evaluate the flux, through that surface. So to find the flux, we need to evaluate those s f dot n ds. This is evaluate over s. Our f is given as 3x 3y z dot our n. Look at this, our n is this thing. So our fx is 2x and negative of fx, so we got 2x negative of ay to 2y, and z is equal to 1, and we have dx dy. Okay, and remember here that we have z, so we need to substitute this z. So with what? With the surface, because given z is equal to, where is it? Z equal to here. Is z equal to those things. So you need to substitute that. So that will give you, having done that, that's what will give you. So we have 3x 3y, and our z is 9 minus x squared minus y squared dot 2x 2y 1 dx dy. This is dy. Okay, now so what we have to try to simplify those things. So we have 6x squared plus 6y squared, okay, 6y squared plus those things, so plus 9 minus, you have those things, x squared plus y squared dx dy. And in fact that you can also write as 6x squared plus y squared. This is x squared, so should we have 5, x squared y squared plus 9 dx dy. Now, having in mind that our S is a circle on xy axis, S is a circle on xy axis, then we can use this transformation. So what left now is we can integrate over the circle, so theta from 0 to 2 pi and arc from 0 to 3. So theta from 0 to 2 pi, arc from 0 to 3, and substitute everything with x and y and dx dy to here. So we have here, you got x squared y squared give you arc squared, so you have 5 arc squared plus 9, okay, and dx dy is r dr d theta, okay. And I think you can solve this. If you proceed that, you might get 5, 6, 7 pi over 2. Please check, yeah, please check. It's not difficult. You can evaluate those integral iteratively. Okay, I'll give you another example. If the surface is not smooth, for example, let's say given f as xy 4yz squared and yz, okay, and S is a cube. S is a cube with vertices 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1. 0, 0, 1, 1, 0, 1, 1, 1, 1, and 0, 1, 1. So if we sketch this surface, so evaluate, integrate as f dot and ds. So if you sketch this cube, this is if you look at those just a cube in the first quadrant, right? So I have 0, 0, 0 is here, 1, 0, 1 here, 1, 1, 0 somewhere here, 0, 1, 1 here, 0, 1, 1, where is 0, 1, 1? X is 0, 1, should be 0, 1, 0 here, sorry, should be 1, 0, 1, 0 here, okay. So for Z1, so we have 0, 0, 1, 0, 0, 1 is here, then 1, 0, 1 should be somewhere here. Oh, right, that, and 1, 0, 1, 1, 1, 1 is somewhere here. That and 1, 0, 1, 1 there. So that. So that's our surface. Okay, that's our surface. So in this case, we can see the surface is not smooth. Then we need to consider each of these surface and evaluate them one by one. Okay, so I will show you not all but a few of them. So let's consider x equal to 0, x equal to 1, y equal to 1, y equal to 0, yeah, z equal to 1, z equal to 0. So we need to consider this surface separately. So 1, 2, 3, 4, 5, 6 we have. So look at here, x equal to 0, which is that, okay, and then you need to consider x equal to 1, x equal to y equal to 1, and so on and so forth. You need to consider for each of that surface. This surface is z equal to 0. This surface, okay, z equal to 0. This surface, z equal to 1. Okay, so that surface at the back there, this is x equal to 0. That surface in front here, this is x equal to 1. This surface here, y equal to 0, and this surface here, this is y equal to 1. So need to consider all these things. Okay, first let's consider surface x equal to 0. If you look at x equal to 0, can we identify n? Can you identify n? X equal to 0, where is x equal to 0? This is x equal to 0, right? So our n is that side. Remember, n is pointed outward. So this is our n. So in this case, our n is negative I. Okay, so our n is negative I. Oh. Alright, and then once we have identified n, then you can just evaluate those our flux S, which is x equal to 0, and what else, f dot n ds, that give you our f is xy 4yz squared yz dot n is negative I, which is negative 1 0 0, yeah, dy dx or dx dy. For x equal to 0 on the surface, x equal to 0 here, so it is obviously that give you 0. Okay, then consider for x equal to 1. We consider x equal to 1. You can evaluate this, yeah, that should give you 0. For x equal to 1, so where is x equal to 1? So that surface, this surface here. Yeah. For x equal to 1, our n is positive I. Our n is positive I. So if you evaluate this, you have s f dot n ds, that give you surface x equal to 0. X equal to 0, which is x from 0 to 1, this surface, yeah, x from 0 to 1, y from 0 to 1, so that give you that surface. So we have here is xy dy dz, x equal to 1, so x equal to 1, this surface. So we don't have I think we don't have z here, right? We don't have y here, Your y is here. So just x and y. So x and z. So should we dy dz? Right, correct. So we have then z from 0 to 1, y from 0 to 1. We got y dy dz. That give you half. Okay. Consider y equal to 1. Y equal to 1. Y equal to 1 is our n is j. Okay, you integrate for this, you integrate over what? You integrate over z0 to 1 x0 to 1. Okay, and y equal to 0 here. Y equal to 0, that you get 0. Y equal to 0. So for this case, y equal to 0, you have your n is negative j, and you integrate over the plane y equal to 0, that gives you 0. Okay, and then you consider y as z equal to 1, that involve x and y. Z equal to 0, that involve x and y. For z equal to 1, you have your integral give you half. For z equal to 0, that give you 0. So if you total up all those things, so therefore you do this, you do this, I show you this one, I show you this one. I show briefly when y equal to 1, that I show briefly when y equal to 0, which is here. I show then for what z equal to 1, z equal to 0, you do it yourself. Okay, so for total, therefore we have zf dot n ds. Yeah, you just add up all these things. You got 0 plus half, 0 plus half, plus for this you got, what is it? I think you got half here, right? For y equal to 1, for you got this one is 4 over 3. Yeah, 4 over 3 plus 4 over 3. Y equal to 0. Y equal to 0, you got 0 plus z equal to 1, you got half. Yeah, you got half. That this is half. Z equal to 0 down here, that you got 0. You got 0. Total. So you total everything, so you got 7 over 3. Okay, so many examples. I give you one more example. Give one more example. Let's say we want to find flux. Flux for f given as zx. This is z squared, x, z squared, x minus 3z, and the surface is S. It's given as z equal to 4 minus y squared, cut by x equal to 0, x equal to 1, and z equal to 0. Okay, and then you need to identify those surface. Just try that. uh, okay, this is a cylinder, and cut by that. So basically we have this kind of cylinder. Okay, so you have this cylinder. So I hope you can see this. So we have this cylinder. Okay, that cylinder. So that surface is given as z equal to 4 minus y squared. So if we project the surface on xy plane, so you basically your r is on xy plane, or what is it? X, this is x is 0 to 1, yeah, and y is 2 minus 2. So basically x from 0 to 1, y minus 2 to 2. Okay, then I think for n ds that you have minus fx minus fy 1 dx dy, so that gives you minus fx is 0, right? Minus fx is 0 there, where here is 0, minus fy is negative 2y, so negative positive 2y, z is 1 dx dy. Then we can evaluate those. S f dot n ds, this is integrate over x. Now our x is x from 0 to 1, y from minus 2 to 2. Okay, our f is given as that, z squared, our z is given as this. Okay, f is z squared, z is given by this, so we have 4 minus y squared, x minus 3z, z is 4 minus y squared, dot nds given by that 0 to y 1 dx dy. Okay, so you can solve this. You got minus 32. What does minus mean? Well, minus means the flux from inside going out. If it's positive, from outside going inside. Okay, now to end this video, let me end up with a few exercises for you that cover many part of my lecture, my video, and not just the video in this section. It's just an exercise for you to try. First, verify Stokes theorem. Verify Stokes theorem for f is minus 3y 3x z4, and s is top portion of ellipsoid, ellipsoid 2x squared plus 2y squared plus z squared equal to 1, cut by z equal to 1 over, I think I've done this one. Number 1 and number 2. There you get. Can you read that? Verify the Stokes theorem for f equal to that as top portion of ellipsoid by that cut by that. Okay. And number 2 we have verify Stokes theorem, as the Stokes theorem, with for f is z squared minus zx, is it? Yeah, zx and y cube, where s is top portion of a sphere, top portion of a sphere, x squared plus y squared plus z squared equal to 1, cut by z equal to 0. Okay, I have some example. 3. If f given as 2x plus y cube, 3xy squared plus 4, show that f is conservative. Show that f is conservative. You know what conservative is. Find f such that f equal to f, and hence evaluate integration from a point 0, 1 to 2, 3 f dot dr. Okay, and number 4, integrate this c 5 xy dx plus x squared dy, okay, where your c is given as y equal to x squared, y equal to 2x. Well, you can use Green theorem. Next, number 5, find flux. For f given as x plus y, z and xz, where s is a cube with vertices plus minus 1, plus minus 1, plus minus 1, and 6. Find flux for f x minus y z, where s is given as a surface of solid bounded by z equal to x squared plus y squared and cut by z equal to 4. So with those exercises, I end up this video here. Thank you.